to now. And I didn't get into any of the troubles of trying to actually project something into the future, because that's going to be a very tough call. But what we're trying to do now is, what about if Earth was bigger and smaller? What about it was cold or really, really hot? What about it was dry or very, very wet? And then the question is also, what is normal? Like, we have a sample of 1. We have our Earth. This is what we call normal right now. But there is something that has been proposed to exist that's called an ocean planet. I figure you guys are very close to the ocean, right? So I assume you go to the ocean every once in a while. And if you just think about it, so the oceans, is there any difference where you go if you go to California or if you actually go to New England? Is there anything that comes into mind?
Temperature.
Right.
Size of the waves.
Size of the waves, the temperature. Now just imagine for a second there's no difference anymore, because what happens is that the continents, you have so much water that all the continents get basically flooded. The whole ocean just covers the whole planet. There's no difference in temperature anymore, because it's basically a nice circulation, and you have just water everywhere. This is a planet that very likely is going to exist because there's a lot of water out in the universe. And so this is one of the other ones we're trying to measure. Huge waves, probably no waves. We'll see. In the middle of the ocean there are some waves, but if you have huge amounts of water, there should be no surface waves anymore. So there should be no difference in temperature. And you look at the world where actually there's so much water that at the bottom of the ocean you have ice, just because of the poor pressure of it. And that's now, it's just one of the completely different worlds that we're looking into and trying to decide how that world would actually announce itself. So we model our worlds, and that includes a lot of educated guessing. One of the other things, though, going back to current work, I told you that we see these planets coming in front and basically dimming the light of the star, right? And by the change in the light curve, by this dip in the light curve, what we can see is the radius of this planet. And this is a very complicated graph, but if we know the mass from the radial velocity, we know how much the star moves, so we know the mass of the planet, and we know the size because the planet goes in front of its star, then we basically can tell you something about the composition. If it's a lot of water, if it's no water. Because if it's only rocky, it's going to be smaller. If it's rocky and it has water, it's going to be bigger. So by knowing the radius and the mass of the planet, we can't tell you much, but we can tell you some of the coarse characteristics. And this is just a movie I wanted to share with you. This is how we envision this whole thing to work. So I told you right now we have a small telescope up in space, and we're going to put a big one up in space, a 1 meter telescope, that looks at all these stars and has a look which ones actually get transited by a planet. So where there's a dip in the light curve. And so it's like, ooh, planet detected. And the better we get, so with the 1 meter telescope in space, we should find all these planets that are Earth size. And then, of course, we're displaying the stars with planets. And this is a complete fictional thing. But we found about more than 200 planets like Jupiter out there, bigger than Jupiter. So who's to say that we're actually not going to be able to see that for Earth? So then we have a look at these planets, and the key signs of life are carbon dioxide, water, ozone in the thermal infrared. So we collect, as you say, you block out the light of the star and you collect the photons from the planet. Here you see there's nothing missing in the curve. So that means it's a dead rock. There's no atmosphere. Well, what about the next one? As we have so many, we're not worried about one. And here you see, ooh, there's something missing in the curve. And the position in the curve where something is missing, where something is absorbed, tells you what chemical it is. So this time it was CO2. And then, of course, this is what we're looking for, Earth. And I tend to say, if you give me that nice a picture, I probably don't need a spectrum anymore, because I can actually tell you that it's blue and pretty. But, you know, it's an artist impression. But here you see there's 3 things missing out of this curve. And that's spectral fingerprints. And the depth of these spectral fingerprints tell you that it's Earth, and also what kind of stage of its evolution it's at. And I just want to, sorry.
I have another question.
Go ahead.
What area of the sky are you looking at? Are you looking at the Milky Way?
What we basically,
Above or
yeah,
below?
what we're basically looking at is just 45 degrees up and down the ecliptic plane.
Okay.
So we could be looking at the whole thing. That would be the idea. But what you have in space, you have a telescope, and you look away from the sun. And so you have your sun shields that only allow you, right now in current design, to go for plus minus 45 degrees anti-sun direction. But there's some other designs on the way that would open up the whole sky. But basically we're looking at a bubble, at a circle around our own sun of 75 light years, and an all really nice and boring stars that are within them. Because we want boring stars, so nothing can happen to the
Not
life on
much
this
on that
planet.
space.
Lisa,
Yeah.
your work is based on space-based observations.
Yes.
Do you coordinate with Jeff Marcy and Earth-based
Yes.
things?
So basically what we had, the planet I was talking about, the 5 times Earth-sized planet, is actually a discovery by the Swiss group. It's like Marcy and Butler. It's Michel Mayor and Didier Queloz, that's the Swiss group. And they found this 5 Earth-mass planet. And so when they found this 5 Earth-mass planets, I get an email. It's like, look, we found something really interesting. Can you do the atmosphere? And I only do the atmosphere for things like Earth. And we think up to about 10 times the mass of Earth, it should be a rocky planet. It could have an atmosphere like ours. If you go about to 15 Earth masses, it more becomes like Jupiter, because when it forms, it just accretes much more gas. So it becomes this, it gets this huge gaseous envelope. But we think if it stays below 10 Earth masses, it could be like our Earth. It would have to be more pressure, it has more gravity. So if we go there, we probably be slack on the ground. And any animals or any life forms that develop, probably more like snakes or something that's actually more ground level, or it has a really good bone structure. But whenever they find something that's interesting, right now, if it's below 10 Earth masses, we are coordinating, and I get an email and I'm trying to actually figure out whether or not they're habitable. This was the first system they found, the Galileo 581c. So I was all excited, and this is why the article came out before they checked it with anybody who does atmospheric modeling. But now for the next one, because we also found that their assumption were not 100% right, for the next one, we're definitely going to get the information first.
Lisa,
Yes.
your spectral indicators presume carbon-based light.
Yes.
How would they be different with silicon-based?
Well, there's a few issues with the question. Very good question, by the way, sorry.
Can you repeat the question? please?
Sorry, yeah, the question was the spectral signatures, or the indicators that I talk about, indicate carbon-based life, basically life like ours. What about if this life was not like ours? What about if it was silicon-based, for example? That's always a very good option. One first answer to this is they seem to be indication that it's silicon-based life. So if you have silicon and carbon, you want to pick carbon to make life out of. Because apparently what happens if you have silicon-based life, it's not so easy to get silicon from one state to the other. So from hard to liquid to gaseous. Apparently it turns out that if you have silicon-based life form, after a while it all gonna solidify. So you lose the ability of life to actually change. But that's a biologist who told me that. The other question is, of course, I would love to look for silicon-based life. If anybody could tell me what I'm looking for. Because definitely if we find a planet that has weird signatures, there's something missing in this curve. And we don't know what it is, so we're saying like, oh, this is weird. We will follow it up. But it's going to be hard enough to actually claim that, see, you have carbon, water, ozone, and methane, and we think there's biology